All right, so let's start our review then. What are some questions that you have, or is there anything on the final review that you want to talk about specifically before we get into any more generic kinds of things? Have we had the opportunity yet to start looking at the review? Okay, that's kind of what I figured. All right, so let's talk about things a little bit more generally here. The final exam is 70 questions. You have 110 minutes to complete those 70 questions. It is going to be a mixture of conceptual questions like the ones that are on the screen right now and calculation questions, things that would require us to do stoichiometry or gas laws or calculations of solution concentrations, all that stuff that we kind of jammed into the month and a half since we came back from fall break. That's all possible in a multiple choice exam like this. Now, what we have to look into and what we have to consider then is, since this is a multiple choice test, chances are pretty good that each of the answers that are there are going to be right if you look at it from a particular point of view. So if you make some kind of mistake in logic, then you could end up arriving at one of these incorrect answers. So from a conceptual standpoint, one of the things that you really want to focus on is you want to make sure that you do have your definitions kind of down pat, that you know conceptually the difference between an atom and a molecule, that you know the difference between a proton and a neutron and an electron in terms of its mass, its charge, its size, where it is in an atom. Because if you don't know your definitions, if you don't know those kind of fundamental building blocks particularly well, then a section like this, which should be relatively easy, will tear you apart. So let's take a look at a couple of these examples and go over kind of what we mean in each of them. So a lot of this stuff harkens back to our chapter 2, but we did see a whole bunch of it just recently in the nuclear chapter. So when we describe, for example, an atom of strontium-90, what do we mean when we see that 90 there? What does that 90 refer to? Yeah, it's the mass number. Okay, what is the mass number? What is mass number? Protons and neutrons. Okay, and so this is different from atomic number, which would be just the proton count. We get the proton count from the periodic table. Strontium is element Sr. So I know that based on that, I have 38 protons. The number of neutrons, well, that would have to be what's left over after I take the 38 out of 90, which would be 52. Now, each of the answers here have in them some kind of logic if you look at it the wrong way. So if you think of 90 as the mass number, but the mass number is just the number of neutrons, then you look at answer B and go, yeah, that kind of makes sense. If you think that the atomic number is the number of neutrons, C and D makes sense. So it really comes down to, again, knowing your definitions and knowing that if we're talking about an atom here, the number of protons and the number of electrons should be the same because atoms are always electrically neutral. If this was changed, if this said an ion of strontium-90, then we would know we have an imbalance of protons and neutrons based on strontium's position on the periodic table. What ion would we expect for strontium? +2. It's in the second column. All the alkaline earth metals form +2 ions. What does a +2 mean? It means I have 2 more protons than electrons. So it is 36, 38, and 52 instead. All right, let's look at number 2. What do these have in common? I've got neon 20, the fluoride 19 ion, and the magnesium 24 ion. Again, based on definitions, immediately, we should throw out letter A. Remember, protons are related directly to the identity of an element. So if they have the same number of protons, they would all be the same element. Obviously, we have 3 different elements there. So what do these 3 have in common? Well, the easiest way to go about it is to start breaking down their structure. So neon is element number 10. It has 10 protons, 10 neutrons, 10 electrons. The fluorine, element number 9, I've got 9 protons, I've got 10 neutrons, and I've got, because of the -1 charge, an extra electron. So after looking at those 2, we've already eliminated protons anyway. Neutrons and electrons are still both the same. Now we gotta go to the magnesium. Magnesium's element number 12, so it's got 12 protons. 24 minus 12 means 12 neutrons, so neutron count's not the same. +2 charge means 2 more protons, 2 fewer electrons. There's my commonality. They all have the same number of electrons. Now, in chapter 3, we gave this particular phenomenon a name. Does anybody remember what we would call these 3 species together? Testing your brains a little bit this morning. Anybody know a geometric prefix that means same? Like in, say, an isosceles triangle. ISO. So this group here is known as an isoelectronic series. I've got three substances with the same number of electrons, isoelectronic. And if you remember again from chapter 3, we talked about a periodic trend in size related to isoelectronic series. Which one of these three would be the biggest? No. I know what you're thinking, and it's the opposite. Okay, let's go back to chapter 3 for a second. What holds together an atom? What makes the electrons stay in the atom as opposed to going out everywhere? Protons. Attraction. The positive center of the nucleus attracts the negative electrons out there in space. As long as there is a sufficient enough attraction between the protons and the nucleus and the electrons out there in those clouds, the electrons stay in the atom. The more attraction that there is, the more that those electrons are going to be drawn in. And so the nucleus that has the greatest charge would also have the greatest attraction. So that, therefore, the magnesium, because it has the most protons, would have the greatest charge, would have the greatest attraction, would be the smallest. The ion that's the biggest, right there in the middle. The fluoride ion would be the largest because it has the fewest protons to attract all those electrons. So naturally, because there's less attraction, there's going to be more repulsion. Those electrons are going to get further away. All right. Let's skip number 3. Again, this is a definition thing. What is an isotope? There's that prefix iso again. So something's the same. What's the same? Same element, same atomic number. What's different? Mass numbers. So the answer here is B. The only one that has the same element, but different mass numbers. All right, this relates directly to what we talked about this week. Which particle, if lost from the nucleus, would not change the atomic number? The neutron, yes. Okay. Obviously, if we lose a proton, that's going to change the atomic number. Remember that alpha particles and beta particles, those radioactive decays that we talked about, we do those transmutation reactions. The thing that we end with is different from the thing that we started with. Either it's lighter and a different element, or in the case of beta decay, it's the same mass, but a different element. Okay? Now let's ask a different question along the same lines. Which one of those decays would occur without changing the mass number? So again, here's where your definitions are going to come in and help you. By definition, a beta particle has no mass. It changes charge, but it doesn't change mass. The beta particle wouldn't change the mass number. It would change the identity, but it wouldn't change the mass. All right, let's go to number 5 here. This is a question out of chapter 2. When alpha particles are shot at a metal foil target to probe the structure of the atom, most passed through without any deflection. Some were deflected at large angles. What did this indicate to Ernst Rutherford, who is credited with this gold foil experiment? C is the correct answer. So yes, that was the main idea. That was the big point that the Rutherford gold foil experiment brought out, is that the atom itself is mostly empty space. After all, most of the alpha particles went straight through. Now, the deflection indicated what? There had to be something dense in the middle that was positively charged to deflect those particles the way that they were. All right. How well do we remember electron configurations? Number 6. An atom has a valence shell configuration of NS1. Which group is it in? Give him a second row. Okay, Ro, you can enlighten us now. It is D for 100. Okay, so 2 things are being asked here. First of all, do you understand the idea of the configuration? And remember, when we're talking about the configurations, we're breaking that periodic table into blocks. The S block being that first 2 columns, the P block being the 6 columns here on the right, the D block being all the transition metals, and the F block being all of these inner transition metals here on the bottom. So from that standpoint then, we would anticipate the transition elements are going to end with something D something. The lanthanides are going to end with something F. And the alkaline earth and alkaline metals, this is where the other part of it comes in. Do you know the difference between the 2? Both are in that S block. The alkali metals are the first column. The alkaline earths are the second column. The first group would be S1. The second group, S2. All right, number 9. The number of unpaired electrons in a gaseous selenium atom is what? So we're going after 2 things here, Lewis dots, and do you know your elements? What element is selenium? It's Se. Okay. Se is in group 16. How many valence electrons are in selenium? Be 6. So if you remember your Lewis dots, we have to draw 6 dots around the selenium, which means that 4 of them would be paired and 2 of them would be unpaired. Now, I want to draw your attention to a term here that will probably show its way into the exam on Monday night. It usually does. Rather than talking about unpaired electrons, exams of this kind love to talk about something called paramagnetism. Paramagnetism, in simple terms, is a magnetic property of substances related to whether or not they have unpaired electrons in them. It's as simple as that. So if I look at the Lewis structure and I see unpaired electrons in it, I know that I'm dealing with something that's paramagnetic. If it is all paired up, that's a phenomenon known as diamagnetism. So unpaired electrons are paramagnetism. All paired electrons are diamagnetism. Now, it does get more complicated than this, but that's not for this course. And the questions that they usually ask you are usually ones that are simple enough that we can look at either an orbital diagram. Remember the electron configuration where we show all the different little orbitals inside of a subshell, or Lewis dots. And that would show us what we need to see. So it's a term that we haven't talked a lot about. I think I maybe mentioned it once way back in chapter 3. Didn't really revisit it since, but I do know that there's a tendency for that term to show up because it's a great way for test takers to kind of weed out who really knows something and who really knows something about chemistry. And so you see that and you can remember it. It's an easy way to get a point. All right, number 10. Which electronic transition is associated with the largest emission of energy? Once again, there are 2 concepts at play in here. If light is going to be emitted from the hydrogen atom, which direction are the electrons going to go? They're going to go from low energy to high, or are they going to go from high to low? High to low. So right away, we can knock out those 2 options. Both of those talk about an electron going from a lower energy level to a higher energy level. And that wouldn't be an emission, that would be an absorption. So right away, by knowing the definition, we've cut it down to a 50-50. It's a coin flip question. Now the question is, what do we know about the energy levels? Are they equally spaced apart? No. Remember, as we get further from the nucleus, the energy levels get closer together. So the first gap, the gap between the first and the second energy levels, is the biggest. The gap between the second and the third is the next biggest. The gap between the third and the fourth is the next biggest. So as we go further from the nucleus, the energy gaps get smaller, which means that that first gap is going to be the biggest gap and will give us the largest amount of energy as a result. All right, number 12 is a quick one. What term best relates hydrogen and deuterium to each other? Right? So there's a lot of terminology in this question. Is deuterium one of the 118 elements on the periodic table? It is not. So therefore, none of the relationships involving same family or anything like that are out. Polymers, we can throw out. Polymers are compounds. Hydrogen and deuterium are both elemental species. Isomers, remember isomers? Those are molecular compounds that have the same chemical formula but different structural arrangements. Again, we're dealing with elemental samples, we can throw that out as well. We're talking about allotropes versus isotopes here. Now we've dealt with both. Does anybody remember what an allotrope is? Think about the sulfur lab. Remember the sulfur lab, we dealt with 3 different forms. We dealt with the orthorhombic form, we dealt with the monoclinic form, we dealt with the lambda form, we dealt with the mu form. All those forms were all sulfur arranged differently in terms of its molecular structure. Right, go down to the atomic level, every single atom inside of them, all sulfurs. That's what allotropes are. Allotropes are elemental samples that have different molecular arrangements to give them slightly different properties. Another good example of that is carbon. Carbon in the form of graphite makes your pencils work. Carbon in the form of diamond makes a substance that is about as hard as anything else can be. Carbon in the form of Buckminster fullerene is the very basis of nanotechnology. Those are allotropes. Hydrogen and deuterium are isotopes. I made mention of this briefly on Wednesday. The 3 different isotopic forms of hydrogen. They're interesting, they're different because they actually are giving 3 different names. Hydrogen for hydrogen 1, deuterium for hydrogen 2, and tritium for hydrogen 3. All right, here's another definition question. What is the maximum number of electrons that can occupy an orbital labeled dxy? Right, show me a number of fingers. 1, 2, 3, 4. How many electrons can fit in the dxy orbital? Okay. Don't let the label confuse you here. It doesn't matter what the label would be. The answer would always be 2.
Oh, yeah.
Maximum number of electrons in any orbital is 2. Now inside of the d sublevel, there are 5 orbitals. And so the sublevel can hold 10 electrons. But each individual orbital can only hold 2 electrons. That becomes the basis of that Pauli exclusion principle. Because the 2 electrons in there have to be 1 up and 1 down, so that we get 4 unique quantum numbers for each electron. Right. Number 16. Which species has this electron configuration? 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. Which one? It's not C. It is zinc, but it's not elemental zinc. Remember, the thing that's missing out of this configuration is the 4s2. For zinc, I would need 4s2 and 3d10 to give it all 30 of its electrons. This configuration only has 28 electrons in it. So your best examples would be either nickel in the elemental state or zinc in the positive 2 state. Both of those would have 28 electrons. Why is it zinc? Well, you have to remember the rules for transition metal ionization. We always take from the highest energy level first. So nickel would have argon 4s2 3d8 as its configuration. Zinc would have 4s2 3d10. And if it was a zinc ion, we take away those 4s2s, it'd be argon 3d10. All right, number 17. Like I warned you a couple of questions ago, here's that term. Now we know what that term means, though. We're looking for unpaired electrons. In particular, we're looking for unpaired electrons in that orbital notation. So what you really want to do is draw out the no gas configuration for each of them, which would be argon. For titanium 4+, titanium would be 4s2 3d2. But if it's 4+, all 4 of those electrons are gone. So how many unpaired electrons do I have in titanium 4? 0, which means titanium 4+ is diamagnetic. Iron 2, well, we start with iron, 4s2 3d6. For iron 2+, we lose these 2 electrons, so we always take from the higher energy level. Do we have unpaired electrons in iron 2? Yeah, we got a lot of them. Therefore, iron 2 plus would be paramagnetic. Now for the zinc, 4s2, 3d10. Any unpaired electrons in zinc? No, it's diamagnetic as well. So this one was diamagnetic, this one was diamagnetic, only the iron 2 was paramagnetic. So like I said, don't be surprised to see a question like that. And if you do, break it down into either orbital notation like this, and you can always cheat and use the noble gas configuration. Or if it's just a simple main group element, put it in its Lewis structure. Put it on its Lewis symbol. All right, any last minute questions before we call this one a day? All right, don't forget about your homework tonight, and if you can make it, Monday at 2 o'clock over in room 125, we'll do all this again. I'll give you 2 hours right before the exam to go over any last minute questions and concepts. Have a great weekend.